Hi, I'm Leif, and in this video we'll be talking about how to use the L-eval application to evaluate your retrieval runs. Now, L-eval is written in Python 3.7 plus, so you'll need that installed, and then you can simply install it by using pip install for L-eval. So here we just go pip install L-eval. I've already installed it, obviously, so it doesn't need to download it. So I have that already, and then I can just check that it works by typing in L-eval. And then it just gives me the usage string. And of course, if I need to get the help, then I can just type in the -h parameter, and it lists out all the different options and arguments that I have. Now, how to use L-eval is fairly straightforward. So if you're familiar with using L-eval, then we try to model it on the same process so that it wouldn't be that different. It takes a gain file and it takes a result file. So the gain file is essentially equivalent to the TREC-QL file. So you can feed in binary relevance judgments. But actually, L-eval is assuming that these values are essentially gain values, whether they're gains of 1 or 0, or 1 or a value between 1 and 0, or above even, right? It will interpret them essentially as a gain value, right? If you have just zeros and ones, then basically you get the binary relevance measurements, right? So to run it, we just type in L-eval. We give it the QL file, right? So these are all going to be binary judgments, and then we have passed in the result file. So here we've just made up a few test files, and then we run through our run the application, and then we can see the output here. So we can see for topic 1, we have a precision of 1 measure. We're pretty good. We get an expected utility of 1, expected total utility of 1. The cost per item is 1. The total expected cost is 1, and the expected number of search items under P at 1 is also 1. Now, of course, I know what those headings are, and so if you wanted to know the headings, you could actually add in the -n, right? And then you can see that it's adding in the column headers for each one, right? You'll also notice that the output is quite different from L-eval if you're familiar with that. It's actually in tab-separated format, so it's easier to read directly into, say, pandas data frames, so then you can do some statistical processing on the results. It also is spitting out a number of measurements for each metric, right? So L-eval will usually spit out a number like expected utility, depending on the measure, right? But it won't tell you all the other values here. And so under the different metrics, you can see that the different values emerge, depending on, if you set the RBP to 0.8, you can see that they're going to a depth of 5, whereas if RBP is 0.2, they're only going to a depth of 1.25 on average, right? And the corresponding expected utility and total expected utility changes quite dramatically depending on how you've set that up. So obviously one of the benefits of the Core framework is that we can also compute these expected costs and total costs, right? But there's two things we need to do in order to facilitate this. We need to say what result type each document is, right? So this is our result file. We have a topic, a dummy. This used to be a dummy column, so we've replaced it with these a place to specify the result item type. Then you can specify the document, its rank, score, and the retrieval run. So now we've set here that we have elements of E2, E1, and so forth. And then we need another file, the cost file, that's going to map this result type to a cost. So here we have E1, 2, 3, and 4. And we have the cost. So here we might say that these are 2.5 seconds to process E1 items, 7.2 to process E2 items, and so on and so forth. Right? And so what we can do then is then add in the C for the cost file. So we add in a -C and then specify the cost file, and then we can recompute all the different measures. So if we do this for the top 5, and then I'll remove the cost file so we can see the difference between the two. So the top one is showing us when we have the cost file into place. And so now you can see that the expected cost and the expected total cost is now different from when we didn't specify the cost file, which is below. So when we don't specify the cost file, Cool-eval assumes there's a unit cost for every item that you look at, and that's why the expected cost is always 1, and then the expected total cost is always that value 1 multiplied by the expected number of items, which gets your expected total cost. Right. But when we have the cost items in, then we can see here that there is quite a difference. So for a P at 4, we're inspecting 4 items, but it's going to cost us about 24 seconds in total, and it's going to take about 6 seconds per item. Whereas if we were under P at 3, then we only look at 3 items, it takes us about 17 seconds, but the expected cost would be about 5.6 seconds on average to process an item. Of course, the expected utility and the expected total utility don't change, but we can work out the rate of gain, so which is then the total, the total expected gain divided by the number of seconds, right? So that would give us the rate of gain, and so then we could work out which is the most efficient, for instance, or compare metrics in terms of the rate of gain. So like I said, we add in the cost file, and then you can use whatever units you'd like. So here we're saying we're assuming time, but some of the other metrics will use a number of characters or a number of terms that they have to read, or you could put dollars and cents associated with it as well. I've already mentioned that we can control the output and output the column names, but we can also output the residuals that Alistair has mentioned as well. So if I specify the residuals, right, and I'll just output that for the first 5 again, then we can see that the output now includes 5 other columns, which are res EU, res ETU, and the res stands for residual. You can see here the values are 0, and that's because we have complete judgments for this little example, right? But if you didn't, then those residuals would then show an output. Now, Cool-eval by default computes some series of standard measures or metrics, but you may want to customize them. And so the way that we do that is by specifying a metrics file, which tells us how we'd like to, or what metrics we'd like to use, and what parameters we'd like to use them. Right, and so once we specify this file, then we can pass it to Cool-eval, and then it will give us the performance. So here's an example where we have our mixed metrics files, and you've got 3 metrics. We'll just grep this just for our first topic. And so now we can see we've customized what metrics we'd like, and then we can see that the different metrics are giving out different expected utilities, different expected total utilities, and they're also taking different amounts of depth and thus time to process. Of course, we didn't add in the cost file, so we could just add that in. And so with the costs now, we can see that under DCG at 10, then where the total cost is probably going to be 30 seconds. It's suggesting. Whereas with RBP, it's saying that they spend about 9 seconds on the page, and under INST, they're saying they spend about 17 seconds on the page. So if we actually have observed data, then we can compare how long they spend on the page compared to how long we predict they'll spend on the page as a way to sanity check our metrics, and another way to triangulate whether we're getting a good estimation of performance, right? So while the expected utility may not be exactly accurate because we might have some missing values and stuff like that, we can certainly observe how long they do spend and how far they do go onto the page. And so we can use these to sort of corroborate how well we're predicting the expected utility and thus expected total utility. Now, within Cool-eval, it does allow you to create a BibTeX file. So for all the different metrics that you use, it will spit out a BibTeX file if you specify the correct flag. So here I'll add in a -b to call it bib.out, and then just run it. So there's all our values. That's fine. And then I will look into our bib file. And so here you can see it just spits out the corresponding BibTeX. So this is for INST, right? This is for RBP, and so forth. And of course, it spits out a reference to the Cool-eval tool. So, if you do use the application, we'd very much appreciate a citation, right, on that front. So just to wrap up, what are the differences between Cool-eval and Trek-eval? Well, when we were doing some compatibility tests between Trek-eval and Cool-eval, we found that Trek-eval reorders the results based on their document scores. So even though you might have put the results in a certain order, it will take the results, resort them according to your score, which may then perturb the ranking that you put in, and then provide the output. So in the cool examples GitHub, we do have some compatibility scripts to compare them, and so we had to do this re-ranking if we wanted to get it to be exactly like Trek-eval. Trek-eval is not gain sensitive, so it's only thinking about binary relevance, but in Cool-eval, if you specify a value of 2, it's interpreted as 2 units of gain. So that means you could get expected utilities greater than 1 if you're using sort of highly relevant documents and representing them as 2s. As you can see, Cool-eval reports all the measures in the same units. That means you can directly compare the estimates between each metrics. And it also reports all the different series of measures and also the residuals in a friendly format, so you can import them into pandas, but you can also see what other predictions the metrics are making, essentially. Okay, that wraps up the video. Remember to like, comment, and subscribe.